What if I told you that the vast majority of our universe, nearly 70% of it, is made up of something we can't see, touch, or even fully understand? Something that acts like an invisible sculptor, silently reshaping the cosmos, stretching it faster and faster every second. That something is dark energy, a mysterious force that has baffled scientists for decades. Since its discovery in the late 1990s, dark energy has been one of the most profound puzzles in modern science. It's not just expanding the universe, it's accelerating that expansion, defying everything we thought we knew about gravity and the fate of the cosmos. But here's the real question. What if dark energy isn't just a passive player in the universe's story? What if it's actively shaping the ultimate destiny of everything: stars, galaxies, even time itself? In this video, we'll dive deep into the mysteries of dark energy, exploring the cutting-edge theories, the mind-bending implications, and the questions that keep astronomers up at night. Strap in, this is going to be a journey that might just change the way you see the universe. In the late 1990s, astronomers made a discovery that completely reshaped our understanding of the cosmos. They were observing distant supernovae, exploding stars that act as cosmic mile markers to measure how fast the universe was expanding. At the time, the prevailing belief was that gravity, the force pulling everything together, would gradually slow down this expansion. But what they found was the opposite. The universe wasn't slowing down at all. It was speeding up. This unexpected result sent shockwaves through the scientific community. If gravity was supposed to be putting the brakes on the universe, what was pushing it to expand faster? The answer was something entirely new, something invisible and mysterious. Scientists called it dark energy, a placeholder term for this unknown force driving the universe apart. This discovery wasn't just a minor tweak to our understanding, it was a complete paradigm shift. The implications were so profound that in 2011, the Nobel Prize in Physics was awarded to the teams behind this groundbreaking work. Their findings revealed that dark energy makes up about 68% of the universe's total energy content, dwarfing even dark matter and ordinary matter. Yet, despite its dominance, dark energy remains one of the greatest mysteries in modern science. So, what exactly is this enigmatic force, and why is it so difficult to pin down? As we explore the nature of dark energy, we'll uncover why it continues to elude even the most brilliant minds in physics. So, what exactly is dark energy? To put it simply, it's one of the greatest mysteries in modern physics. Unlike anything we can see, touch, or measure directly, dark energy is the name we've given to the mysterious force that's causing the universe to expand at an accelerating rate. But what could this force actually be? Scientists have been grappling with this question for decades, and while we don't have a definitive answer, there are a few leading theories that attempt to explain its nature. One of the most prominent ideas is the cosmological constant, a concept first proposed by Albert Einstein over a century ago. Einstein introduced this term as a kind of balancing act in his equations to describe a static universe. But when it was later discovered that the universe wasn't static, it was expanding, the cosmological constant took on a new meaning. Today, it's thought of as a repulsive force, a kind of energy woven into the fabric of space itself that pushes galaxies apart. Think of it like an invisible wind, gently but relentlessly driving the cosmos to stretch further and further. Another intriguing theory is quintessence, a dynamic field that changes over time. Unlike the cosmological constant, which is steady and unchanging, quintessence suggests that dark energy might vary in strength or even direction as the universe evolves. Imagine it as a cosmic tide, sometimes stronger, sometimes weaker, but always influencing the way the universe grows. This idea opens up fascinating possibilities. but it also raises new questions about how such a field would behave and interact with the rest of the cosmos. Now, it's important to note that dark energy isn't the same as dark matter, even though they both share the word dark. Dark matter is a mysterious substance that doesn't emit light but exerts gravitational pull, helping to hold galaxies together. Dark energy, on the other hand, is the force driving those galaxies apart. One is about attraction, the other about repulsion. Two sides of the cosmic coin, each playing a critical role in shaping the universe as we know it. To visualize dark energy's effect, picture a balloon being inflated. As the balloon expands, the dots on its surface representing galaxies move further apart. Dark energy is like the air being pumped into that balloon, stretching space itself and accelerating the expansion. It's a subtle but profound force, one that's reshaping the cosmos on the grandest scales. But what does this mean for the universe as a whole? How does dark energy's influence play out over billions of years? That's where things get even more fascinating as we explore how this enigmatic force is shaping the fate of everything around us. Now, let's zoom out and consider the bigger picture literally. Dark energy isn't just a mysterious force lurking in the shadows of the cosmos. It's the driving engine behind one of the most profound phenomena in the universe, the accelerated expansion of space itself. Picture this: galaxies are like dots on a rubber sheet, and dark energy is stretching that sheet faster and faster over time. The farther apart those dots are, the faster they seem to move away from each other. This isn't just a whimsical analogy, it's a reality that astronomers have been measuring for decades. At the heart of this discovery lies something called the Hubble constant. Named after the astronomer Edwin Hubble, this constant represents the rate at which the universe is expanding. By observing distant galaxies and measuring how quickly they're moving away from us, scientists have been able to calculate this rate. But here's the twist: the expansion isn't just happening, it's speeding up, and that's where dark energy comes into play. It's the invisible force pushing the universe apart, counteracting gravity's pull and ensuring that galaxies aren't just drifting apart but accelerating into the void. The implications of this are staggering. Over billions of years, galaxies will become so far apart that they'll no longer be visible to one another. Imagine a future where the night sky is empty, where even the closest galaxies have vanished beyond the horizon of the observable universe. It's a lonely cosmic fate, but one that underscores the sheer power of dark energy. This relentless expansion doesn't just shape the universe's future, it also gives us clues about its past and present structure. And speaking of structure, this brings us to an even grander question. How does dark energy influence the universe's large-scale architecture? From the cosmic web of galaxies to the vast voids between them, dark energy's fingerprints are everywhere. But to truly understand its role, we need to dive deeper into how it shapes the fabric of the cosmos itself. When we talk about dark energy, it's easy to focus on its role in accelerating the expansion of the universe. But its influence goes far beyond that. Dark energy also plays a critical role in shaping the universe's large-scale structure, often called the cosmic web. Picture the universe as a vast, intricate network, with galaxies and galaxy clusters connected by long, delicate filaments of dark matter and gas. These filaments form the backbone of the cosmic web, creating a sprawling, interconnected framework that spans the cosmos. And nestled between these filaments are enormous voids, vast, empty regions that seem almost unnaturally quiet compared to the bustling activity of galaxies. This is where dark energy steps in. As the universe expands, dark energy doesn't just push galaxies apart, it also stretches these voids, making them even larger over time. Think of the cosmic web like a sponge. The filaments are the sponge's solid structure, while the voids are the holes. Dark energy is like someone pulling on that sponge, stretching it out and expanding the holes further and further. The result is a universe where the voids grow larger and the filaments, though still strong, become more spread out. Over billions of years, this process has fundamentally reshaped the distribution of matter in the universe, creating the cosmic web we observe today. But why does this matter? The cosmic web isn't just a fascinating structure, it's also a record of the universe's history. By studying how dark energy has influenced its formation, we can trace how the universe has evolved over time. And that's not all. The cosmic web also affects how galaxies form and grow. Galaxies along the filaments have access to more gas and dark matter, giving them the fuel they need to thrive. Meanwhile, galaxies in the voids are isolated, often stunted in their growth. This delicate balance between the filaments and the voids is a direct consequence of dark energy's relentless push. Now, as we've seen how dark energy shapes the universe today, it's worth asking, how did it all begin? What role did dark energy play in the early universe, and how did it influence the seeds of the cosmic web we see now? That's where our journey takes us next. But let's rewind the cosmic clock far, far back to a time when the universe was just a fraction of a second old. This is the era of cosmic inflation, a mind-bending moment when space itself expanded faster than the speed of light. And here's where things get even more intriguing. Some scientists suggest that dark energy, or something very much like it, might have been the driving force behind this incredible burst of growth. Think of it this way: if the universe today is like a balloon slowly being inflated by dark energy, the early universe was that same balloon undergoing a sudden, explosive stretch. Inflation theory tells us that during this brief but critical period, space-time expanded exponentially, smoothing out the cosmos and setting the stage for everything we see today. It's almost as if dark energy, or its ancient predecessor, was laying the groundwork for the universe's structure long before galaxies, stars, or even atoms existed. Now here's the fascinating parallel. Just as dark energy is causing the universe to expand faster today, something similar may have powered inflation. This raises a tantalizing question: could dark energy be a remnant of that primordial force, lingering in the fabric of space-time even now? While we don't have all the answers, the idea bridges the gap between the universe's fiery beginnings and its mysterious future. And speaking of beginnings, this brings us to the next piece of the puzzle. How does dark energy connect to the Big Bang itself? After all, the Big Bang wasn't just an explosion, it was the birth of space, time, and everything in between. Could dark energy have been there from the very start, shaping the universe in ways we're only beginning to understand? Let's explore that next. To understand dark energy and its role in the universe, we need to rewind the cosmic clock all the way back to the Big Bang. This explosive event, which occurred around 13.8 billion years ago, marks the birth of everything we know: space, time, matter, and energy. In those early moments, the universe was a seething, dense soup of particles and radiation, expanding rapidly. But something fascinating happened billions of years later. Dark energy emerged as a dominant force, quietly shaping the cosmos in ways we're still trying to fully grasp. For the first few billion years after the Big Bang, gravity was the star of the show. It pulled matter together, forming galaxies, stars, and planets. But as the universe continued to expand, something unexpected occurred. Around 5 billion years ago, dark energy began to take over. Unlike gravity, which pulls things together, dark energy pushes space itself apart, acting like an invisible force that accelerates the universe's expansion. This shift from gravity's dominance to dark energy's reign marked a turning point in cosmic history. To put it into perspective, imagine the universe as a balloon. Right after the Big Bang, the balloon was inflating rapidly, but the material on its surface, representing matter, was still clumping together due to gravity. As time went on, the balloon kept expanding, and the space between those clumps grew larger. But then, dark energy kicked in, like someone suddenly blowing air into the balloon faster and faster. The clumps of matter were still there, but the space between them began stretching at an ever-increasing rate. This is what we're observing today, galaxies moving away from each other faster and faster, with dark energy driving the acceleration. Now, here's where things get even more intriguing. Scientists often talk about a concept called critical density. This is the precise amount of energy and matter needed to determine the universe's ultimate fate. If the density were too high, gravity would eventually pull everything back together in a big crunch. If it were too low, the universe would expand forever, growing colder and more sparse. Dark energy has tipped the scales, pushing the universe toward a future where expansion not only continues but accelerates. This means the universe is likely heading toward what's called a big freeze, where galaxies drift so far apart that the cosmos becomes a vast, cold emptiness. But what does this mean for us? While these events unfold on timescales far beyond human comprehension, they remind us of the profound and mysterious forces at work in the cosmos. Dark energy didn't just appear out of nowhere. It's been part of the universe's story since the beginning, even if its effects only became noticeable much later. And as we continue to study it, we're not just uncovering the universe's past, we're also glimpsing its future. So, what does the future hold under dark energy's influence? Will the universe keep expanding forever, or could there be other forces at play we haven't yet discovered? That's where our journey takes us next, as we explore the ultimate fate of the universe and the role dark energy plays in shaping it. So, what does the future hold for our universe? The answer lies in the mysterious influence of dark energy, a force so powerful it's shaping the destiny of everything we know. Picture this: trillions of years from now, galaxies drifting further and further apart, their light fading into an ever-expanding void. This is the Big Freeze, one of the most widely accepted scenarios for the universe's ultimate fate. As dark energy continues to accelerate the expansion of space, the cosmos grows colder, darker, and emptier until even the last remnants of stars flicker out. It's a chilling thought, isn't it? A universe where nothing is left but the faintest whispers of heat fading into absolute stillness. But that's not the only possibility. Imagine a far more dramatic end, the Big Rip. In this scenario, dark energy doesn't just push galaxies apart. It becomes so dominant that it rips through the fabric of space itself. Galaxies are torn apart, then stars, then planets, and eventually even atoms are pulled to pieces. It's as if the universe itself is unraveling, layer by layer, until nothing remains but a sea of disconnected particles. This catastrophic ending is like the ultimate cosmic explosion, but instead of energy and light, it leaves behind only chaos and silence. These scenarios might sound like science fiction, but they're grounded in real scientific theories and observations. The key lies in understanding how dark energy behaves over time. Will it continue to push the universe apart at a steady rate, leading to the Big Freeze? Or will its influence grow stronger, eventually triggering the Big Rip? These questions aren't just about distant futures, they're about understanding the very nature of the cosmos we live in today. But here's the catch: studying dark energy is no easy task. It's invisible, elusive, and incredibly subtle in its effects. So how do scientists even begin to unravel its secrets? That's where the challenges come in. Challenges we'll explore next, as we dive into the tools and methods researchers use to study this enigmatic force. From cutting-edge telescopes to groundbreaking experiments, the quest to understand dark energy is one of the most thrilling adventures in modern science. And the answers we find could change everything we know about the universe. Studying dark energy is one of the most perplexing challenges in modern cosmology. Unlike stars, planets, or even black holes, dark energy doesn't emit light, absorb radiation, or interact with matter in any way we can directly observe. This means scientists can't point a telescope at it or capture it in a lab. Instead, they're left to piece together clues from its effects on the universe itself. Imagine trying to study something invisible, intangible, and seemingly everywhere at once. It's like solving a cosmic mystery with only the faintest of footprints to guide you. One of the biggest hurdles is the sheer scale of dark energy's influence. It's not just a small force tucked away in some corner of the universe, it's shaping the entire cosmos. To understand it, researchers must look at the largest structures in existence: galaxies, clusters of galaxies, and even the vast voids between them. But here's the catch: these observations are incredibly complex. Light from distant galaxies takes billions of years to reach us, and by the time it does, the universe has expanded even further. This makes it difficult to measure distances accurately and understand how dark energy has changed over time. Another challenge is the precision required. Dark energy's effects are subtle, influencing the universe's expansion rate by just a fraction of a percent over millions of years. Detecting such minute changes demands instruments of extraordinary sensitivity and long-term observations. Even the smallest errors in measurement can lead to wildly different conclusions about dark energy's nature. It's like trying to weigh a feather on a scale that's constantly shifting. To overcome these obstacles, scientists rely on indirect methods. One of the most powerful tools is observing supernova, the explosive deaths of massive stars. By measuring how bright these supernovae appear from Earth, researchers can calculate how far away they are and how the universe's expansion has stretched their light over time. Another key method involves studying the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light holds clues about the universe's early expansion and how dark energy has influenced it since. But even with these techniques, there's still so much we don't know. Is dark energy constant, or does it change over time? Could it be tied to some undiscovered field or particle? These questions push the boundaries of our current technology and understanding. Thankfully, the scientific community isn't giving up. In fact, they're building some of the most advanced tools ever conceived to tackle this cosmic puzzle head-on. Next, we'll explore the groundbreaking missions and instruments designed to shed light on the mysteries of dark energy. To truly understand dark energy, we need more than just theories. We need tools that can peer into the deepest corners of the universe. Enter the Dark Energy Survey, a groundbreaking project that has been mapping millions of galaxies since its launch. Using a powerful camera mounted on a telescope in Chile, this mission has captured the distribution of galaxies across vast cosmic distances, helping scientists measure how the universe's expansion has changed over time. But it's not just about mapping, it's about uncovering patterns that reveal the invisible hand of dark energy shaping the cosmos. Then there's the Euclid Space Telescope, a European Space Agency mission that's set to take this exploration even further. Scheduled to launch in the near future, Euclid will create a 3D map of the universe covering more than a third of the sky. By studying the way galaxies cluster and how light bends around massive objects, a phenomenon known as gravitational lensing, Euclid aims to provide unprecedented insights into dark energy's influence on the universe's structure. And let's not forget the Nancy Grace Roman Space Telescope, NAS, a next-generation observatory named after the pioneering astronomer who helped shape modern space science. This telescope will focus on measuring the distances to thousands of supernovae and mapping the distribution of galaxies across cosmic history. Its mission to answer one of the biggest questions in astronomy: why is the universe speeding up, and what role does dark energy play in this acceleration? These missions are more than just technological marvels. They're our best chance to decode the mysteries of dark energy. By piecing together data from these projects, scientists hope to build a clearer picture of how dark energy has influenced the universe's evolution from its earliest moments to the present day. And speaking of supernova, these cosmic explosions have their own unique story to tell about dark energy, a story we'll dive into next. So, how do we measure something as vast and mysterious as the expansion of the universe? Enter Type Ia supernova, the cosmic beacons that light the way. These stellar explosions are incredibly special because they all shine with nearly the same peak brightness. Think of them like lighthouses in the night sky, each one emitting a predictable amount of light no matter where they're found. This consistency makes them what astronomers call standard candles. By observing how bright a Type Ia supernova appears from Earth, scientists can calculate its distance with remarkable precision. It's like knowing exactly how bright a light bulb is supposed to be and using that to figure out how far away it is just by how dim it looks. But Type Ia supernova aren't just useful for measuring distances. They've played a starring role in one of the most groundbreaking discoveries in modern cosmology: dark energy. In the late 1990s, astronomers studying these supernovae made a startling observation. They found that the universe wasn't just expanding, it was accelerating. Distant supernovae were fainter than expected, meaning they were farther away than predicted. This unexpected result pointed to something invisible: dark energy pushing the universe apart faster and faster over time. Without these cosmic explosions, we might never have uncovered this mysterious force shaping the fate of the cosmos. Today, Type Ia supernova remain a cornerstone of astronomical research. They're not just relics of the past, they're active tools helping us refine our understanding of the universe's expansion. Every new supernova observed adds another piece to the puzzle, allowing scientists to test theories and refine measurements of dark energy's influence. But while supernovae have been invaluable, they're just one piece of the cosmic story. To truly understand dark energy, we need to look beyond these stellar explosions to another key piece of evidence: the faint afterglow of the Big Bang itself. Up next, we'll explore the cosmic microwave background and how it connects to the mystery of dark energy. The universe has a story to tell, and one of its most profound chapters is written in the faint glow of the cosmic microwave background, or CMB. This ancient light, often described as the afterglow of the Big Bang, is like a cosmic time capsule, preserving the conditions of the universe just 380,000 years after its birth. Picture this: a universe so young that it hadn't yet formed stars or galaxies, filled instead with a hot, dense plasma that glowed with intense energy. As the universe expanded and cooled, this light was set free, stretching over billions of years to become the faint microwave radiation we detect today. What makes the CMB so extraordinary is that it's not just a relic of the past, it's a treasure trove of information. Embedded within its subtle patterns are clues about the universe's composition, including the mysterious force we call dark energy. When scientists map the CMB, they're looking at tiny temperature fluctuations, areas that are slightly hotter or colder than the average. These fluctuations are like cosmic fingerprints, revealing the distribution of matter and energy in the early universe. They tell us how matter clumped together, how structures like galaxies began to form, and how the universe has expanded over time. But here's where dark energy comes into play. By studying these temperature variations, scientists can trace how the rate of the universe's expansion has changed. The CMB shows us that in the early universe, gravity dominated, slowing down the expansion. But over billions of years, something flipped the script. Dark energy began to push the universe apart faster and faster. This acceleration is etched into the CMB's patterns, giving us a glimpse of dark energy's influence on the cosmos. Now, if the CMB is the universe's baby picture, galaxy clusters are like its teenage years, a stage where the effects of dark energy become even more apparent. These massive structures, formed by the gravitational pull of dark matter, are directly shaped by the universe's expansion. As we move forward, we'll explore how galaxy clusters act as cosmic signposts, helping us measure the impact of dark energy and unravel its secrets. Galaxy clusters are like cosmic metropolises, vast collections of galaxies bound together by gravity, some containing thousands of members. These colossal structures are not just awe-inspiring, they're also critical tools for unraveling the mysteries of dark energy. Because they're the largest gravitationally bound systems in the universe, their formation and evolution are deeply tied to the expansion of space itself. When we study galaxy clusters, we're essentially looking at the fingerprints dark energy has left on the cosmos over billions of years. One way scientists use galaxy clusters to probe dark energy is by examining their distribution across the universe. Imagine the universe as a giant web with clusters sitting at the intersections of filaments of dark matter. By mapping where these clusters are and how densely they're packed, researchers can trace the rate at which the universe has expanded over time. Dark energy, which drives this acceleration, leaves its mark on the spacing between clusters. The more spread out they are, the stronger the evidence that dark energy has been at work, pushing galaxies apart. But how do we actually measure these clusters? One powerful technique is gravitational lensing. When light from distant galaxies passes near a galaxy cluster, the immense gravity of the cluster bends the light, acting like a cosmic magnifying glass. This distortion allows astronomers to map the cluster's mass, including the invisible dark matter that makes up most of its structure. Another method involves X-ray observations. Galaxy clusters are filled with hot gas that emits X-rays, and by studying this radiation, scientists can estimate the cluster's mass and how it changes over time. Together, these techniques paint a detailed picture of how clusters grow, or don't grow, in a universe dominated by dark energy. What's fascinating is that galaxy clusters are like time capsules. By observing clusters at different distances and therefore different points in the universe's history, we can see how their growth has been stunted by dark energy's influence. In the early universe, gravity had the upper hand, pulling matter together to form clusters. But as dark energy took over, it began to counteract gravity's pull, slowing the growth of these massive structures. This tug-of-war between gravity and dark energy is written into the history of galaxy clusters, and by decoding it, we're getting closer to understanding the true nature of dark energy. As we piece together the story of galaxy clusters, we're also building toward a deeper question. What is the equation of state for dark energy? This concept, which describes how dark energy's density changes over time, could hold the key to unlocking one of the greatest mysteries in cosmology. But to explore that, we'll need to dive into the physics behind dark energy itself. So, how do scientists quantify something as elusive as dark energy? This is where the equation of state comes into play. Think of it as a kind of cosmic fingerprint, a parameter that helps us understand how dark energy behaves over time. This parameter, often represented by the letter W, is crucial because it tells us how dark energy's density evolves as the universe expands. If W equals -1, it suggests that dark energy is constant, unchanging over time, a concept tied to what we call the cosmological constant, an idea originally proposed by Einstein. But what if W isn't exactly -1? What if it's slightly higher or lower? That's where things get fascinating. A value greater than -1 might indicate that dark energy is weakening over time, while a value less than -1 could mean it's growing stronger. These subtle differences could have profound implications for the fate of the universe, whether it continues expanding forever. accelerates even faster or perhaps even collapses one day. But here's the kicker, we still don't know the exact value of W. Current observations are incredibly precise, yet they leave room for debate. Is dark energy truly constant, or is it evolving? This uncertainty is what keeps scientists on their toes, constantly refining their models and searching for clues in the cosmos. And while the equation of state gives us a framework to work with, it also raises more questions than it answers. What if dark energy isn't the only player in this cosmic game? What if there's more to the story? That's where alternative theories come into the picture, ideas that challenge our current understanding and open up entirely new possibilities. But that's a conversation for the next part of our journey. But what if dark energy isn't the only explanation for the universe's accelerating expansion? Some scientists propose alternative ideas that challenge the very existence of dark energy, suggesting that our understanding of gravity itself might need an update. These theories, collectively known as modified gravity theories, offer a different lens through which to view the cosmos. Instead of invoking an unseen force like dark energy, they suggest that gravity behaves differently on cosmic scales than we currently think. One of the most well-known modified gravity theories is called modified Newtonian dynamics, or MND. This idea proposes that gravity doesn't follow the rules laid out by Newton or Einstein when dealing with extremely large distances. Instead, it suggests that gravity weakens less quickly over vast cosmic scales, which could explain why galaxies and galaxy clusters appear to be moving apart faster than expected. Another approach, called scalar tensor theories, introduces additional fields that interact with gravity, altering its behavior in ways that mimic the effects of dark energy. These alternatives have their strengths. For one, they don't require the existence of a mysterious, invisible energy that makes up nearly 70% of the universe. They also offer a more elegant solution for some of the anomalies that dark energy struggles to explain, such as the precise rate of the universe's expansion. However, they're not without their challenges. Modified gravity theories often struggle to account for all the observations that dark energy neatly explains, like the distribution of matter in the early universe or the patterns seen in the cosmic microwave background. While these ideas are fascinating, they remain controversial. The debate between dark energy and modified gravity is far from settled, and it's a reminder of how much we still have to learn about the cosmos. But whether it's dark energy or a new understanding of gravity that ultimately explains the universe's expansion, one thing is certain: the answer will reshape our understanding of reality itself. And speaking of reshaping reality, what if dark energy isn't just shaping our universe but countless others? That brings us to the multiverse theory, where dark energy might play a role far more profound than we ever imagined. What if our universe isn't the only one out there? What if the mysterious force we call dark energy is just one piece of a much larger cosmic puzzle? This brings us to one of the most fascinating and speculative ideas in modern cosmology, the multiverse. Imagine for a moment that our universe is just one of countless others, each with its own unique properties. And in this vast cosmic garden, dark energy might be the key that determines how these universes grow and evolve. Think of it like this: picture a garden filled with different types of plants. Some grow tall and strong, others remain small, and a few might even wither away. Now replace those plants with universes. In this cosmic garden, dark energy acts like the soil. It provides the foundation that shapes how each universe develops. Some universes might have just the right amount of dark energy, allowing them to expand at a steady pace, fostering the formation of galaxies, stars, and maybe even life. Others might have too little, causing them to collapse in on themselves too quickly. And then there are those with too much dark energy, expanding so rapidly that matter never has a chance to clump together, leaving them cold, empty, and barren. This idea isn't just science fiction, it's rooted in some of the most advanced theories in physics. The concept of the multiverse suggests that our universe might be one of many, each with its own unique set of physical laws and constants. Dark energy could be one of those variables differing from universe to universe, and this variation might explain why our universe seems so finely tuned for life. If there are countless universes out there, it's possible that only a small fraction have the right conditions for life to emerge. We just happen to be in one of them. But here's where it gets even more intriguing. If dark energy plays such a crucial role in shaping the fate of universes, what does that mean for the existence of a multiverse? Could dark energy be a bridge between these parallel realities, or is it simply a byproduct of the underlying physics that governs them? These questions take us to the edge of what we know and what we can even imagine. And as we ponder these possibilities, we're left with a deeper question. What does it mean for us living in this one universe to exist in a reality that might be just one of many? This leads us to the next layer of the mystery, the philosophical implications of dark energy. What does its existence tell us about the nature of reality itself? Dark energy doesn't just challenge our scientific framework, it forces us to confront some of the most profound philosophical questions humanity has ever asked. What does it mean to live in a universe that's not only expanding but accelerating away from itself? If the cosmos is stretching faster and faster, what does that say about the nature of reality itself? Are we witnessing the universe's grand design, or is this simply a cosmic accident, a quirk of physics we're only beginning to grasp? These questions go beyond the realm of equations and data. They touch on something deeper: our place in the cosmos. For centuries, humanity has looked to the stars and wondered if we're alone, if we're significant, or if we're just a fleeting moment in an indifferent universe. Dark energy adds another layer to that mystery. It's a reminder that even with all our technological advancements, there are still fundamental truths about existence that elude us. It's humbling, isn't it, to realize that we're part of something so vast, so unknowable, that it defies even our most sophisticated theories. And then there's the question of purpose. If the universe is destined to expand forever, accelerating into a cold, dark emptiness, what does that mean for the stories we tell ourselves about meaning and destiny? Are we just temporary flickers of life in an infinite void, or is there something more to our existence? These aren't questions with easy answers, but they're the kind of questions dark energy forces us to grapple with. It's not just a scientific curiosity, it's a mirror reflecting back our deepest uncertainties and aspirations. But here's the thing, while dark energy might highlight the limits of our knowledge, it also underscores the beauty of curiosity. It's a reminder that the universe is full of mysteries waiting to be explored, and that the act of asking questions, even if we don't have all the answers, is what makes us human. So, as we ponder the philosophical implications of dark energy, let's also celebrate the fact that we're here in this moment trying to make sense of it all. And speaking of making sense, let's shift our focus to something equally fascinating: how dark energy has influenced our culture and imagination. From science fiction to art, dark energy has sparked creativity in ways that go far beyond the equations of physics. But more on that in just a moment. Dark energy isn't just a mystery for scientists, it's also a source of endless fascination for storytellers, filmmakers, and artists. In science fiction, dark energy often takes on a life of its own, becoming a plot device that unlocks unimaginable possibilities. Think about movies where characters harness dark energy to power interstellar travel, or books where it serves as the key to unraveling the secrets of the universe. These portrayals tap into our collective curiosity about the unknown, reflecting humanity's desire to explore what lies beyond the edges of our understanding. Take, for example, the way dark energy is depicted in popular sci-fi franchises. It's often portrayed as a mysterious, almost magical force, something that defies the laws of physics as we know them. This creative interpretation isn't just about entertainment. It's a reflection of our awe and wonder at the vastness of the cosmos. By weaving dark energy into their narratives, writers and filmmakers invite us to dream bigger, to imagine a reality where the boundaries of science are pushed to their limits. But it's not just about fiction. Artists, too, have been inspired by the concept of dark energy, using it as a metaphor for the unseen forces that shape our lives. Paintings, sculptures, and even music have explored the idea of an invisible yet powerful energy that drives the universe forward. These creative expressions remind us that science and art aren't so different. Both are driven by a desire to make sense of the world around us, even when that world is filled with mysteries we can't yet solve. This cultural fascination with dark energy also highlights something deeper: our innate need to explore the unknown. Whether it's through a blockbuster movie or a thought-provoking novel, dark energy serves as a reminder that the universe is full of questions waiting to be answered. And while we may not have all the answers yet, the journey of discovery is just as thrilling as the destination. Speaking of discovery, the intrigue surrounding dark energy doesn't stop at the realms of art and storytelling. It also has real-world implications, driving scientific research that could revolutionize our understanding of the cosmos and even our daily lives. Up next, we'll explore how dark energy research is shaping technology and economics, opening doors to innovations that could change the way we live, work, and explore the universe. The pursuit of understanding dark energy isn't just a scientific endeavor. It's a catalyst for innovation that ripples across industries and economies. Think about it. To study something as elusive as dark energy, we've had to push the boundaries of technology to its absolute limits. This has led to groundbreaking advancements in telescopes, detectors, and data analysis tools that are nothing short of revolutionary. For instance, the development of ultra-sensitive detectors capable of capturing the faintest signals from the depths of space has not only deepened our understanding of the cosmos, but also paved the way for breakthroughs in medical imaging. Technologies born from dark energy research are now being used to detect early signs of diseases with unprecedented precision, and it doesn't stop there. The massive amounts of data generated by dark energy experiments have driven innovations in computing and artificial intelligence. Algorithms designed to sift through cosmic data are now being applied to solve complex problems in fields like finance, climate modeling, and even urban planning. The economic impact is equally profound. Investments in dark energy research create high-tech jobs, foster collaboration between industries, and inspire the next generation of scientists and engineers. It's a reminder that the quest to understand the universe doesn't just expand our knowledge, it fuels progress here on Earth. But as we marvel at these advancements, it's worth pausing to consider the broader implications. What are the ethical responsibilities that come with such powerful technologies? How do we ensure that the tools we create to explore the cosmos are used responsibly here on our own planet? These are the questions we'll tackle next as we delve into the ethical considerations surrounding dark energy research and its far-reaching consequences. As we continue to unravel the mysteries of dark energy, it's impossible to ignore the ethical questions that come with such groundbreaking research. How much of our collective resources should be devoted to understanding something as abstract as dark energy, especially when there are pressing, tangible problems here on Earth? This isn't just a question of funding, it's about priorities. Should we invest billions in telescopes and space missions to study the cosmos? Or should that money go towards solving issues like climate change, poverty, or healthcare? The truth is, these aren't mutually exclusive goals, but they do force us to think deeply about how we allocate our resources as a society. Curiosity-driven science has always been the backbone of human progress. After all, it was the pursuit of seemingly abstract questions that led to discoveries like electricity, relativity, and even the internet. But with dark energy, we're dealing with something that, at least for now, doesn't have immediate practical applications. So, is it worth it? The answer might lie in understanding that science isn't just about solving today's problems, it's about preparing for tomorrow's. Without exploring the unknown, we risk stagnating as a species. Still, it's a delicate balance and one that requires careful consideration. And then there's the question of responsibility. Scientists studying dark energy hold immense power in how they communicate their findings. Imagine discovering something that could fundamentally change our understanding of the universe. How do you share that with the public without causing unnecessary fear or confusion? Miscommunication can lead to misinformation, and in a world already fraught with scientific skepticism, the stakes are high. Scientists have a duty not just to discover, but to educate, to inspire, and to ensure their work is understood in the right context. These ethical dilemmas don't have easy answers, but they're essential to grapple with as we push the boundaries of human knowledge. And speaking of pushing boundaries, one of the most exciting aspects of dark energy research is how it brings the world together. Which leads us to the next chapter in this story, the role of international collaboration. When it comes to tackling something as vast and complex as dark energy, no single country can do it alone. The next frontier of discovery might just depend on how well we can work together across borders, cultures, and disciplines. The quest to unravel the mysteries of dark energy isn't just a scientific challenge, it's a global endeavor. From the bustling labs of Europe to the remote observatories in the Chilean Andes, researchers from every corner of the world are joining forces to shed light on this enigmatic force. It's a story of collaboration that transcends borders, uniting scientists across cultures, languages, and disciplines in a shared mission to understand our universe. One of the most remarkable examples of this international teamwork is the Dark Energy Survey, or DES. This ambitious project brought together over 400 scientists from 25 institutions spanning 7 countries. Using a state-of-the-art camera mounted on a telescope in Chile, DES mapped hundreds of millions of galaxies, creating one of the most detailed maps of the cosmos ever made. But it wasn't just about the technology, it was about the people. Researchers from the United States, Brazil, Spain, and beyond worked side by side, pooling their expertise to analyze the data and push the boundaries of our understanding. Then there's the Euclid mission, a collaboration led by the European Space Agency with contributions from NASA and scientists across the globe. Euclid's goal is to create a 3D map of the universe stretching back over 10 billion years. By studying the distribution of galaxies and the subtle distortions in their light caused by dark energy, Euclid aims to uncover clues about how the universe has expanded over time. It's a project that wouldn't be possible without the combined efforts of thousands of scientists, engineers, and technicians from dozens of countries. What makes these collaborations so powerful is the diversity of perspectives they bring. When researchers from different backgrounds come together, they approach problems in unique ways, sparking innovation and accelerating progress. It's a reminder that science, at its core, is a universal language, one that fosters unity even as it seeks to answer the most profound questions about our existence. And as we look to the future, this spirit of cooperation is only growing stronger. The next frontier in dark energy research isn't just about professional scientists, it's about involving everyone. From classrooms to living rooms, people around the world are contributing to this grand effort through citizen science projects. But more on that in just a moment. What if I told you that you don't need a PhD or a telescope to help unravel the mysteries of dark energy? Believe it or not, some of the most groundbreaking discoveries in modern astronomy are being made with the help of everyday people just like you. This is the power of citizen science, a movement that's revolutionizing how we explore the universe. One of the most well-known projects is Galaxy Zoo, an online platform where volunteers from all over the world can help astronomers classify galaxies. By simply looking at images and answering questions like, is this galaxy spiral or elliptical, or does it show signs of merging with another galaxy? You're contributing to real scientific research. This data is invaluable for astronomers studying how galaxies evolve over time, a key piece of the dark energy puzzle. And the best part, no prior knowledge is required. All you need is curiosity and a willingness to learn. But Galaxy Zoo is just the beginning. There are dozens of other citizen science projects focused on cosmology and dark energy. Some involve analyzing patterns in the distribution of galaxies, while others track supernova exploding stars that serve as cosmic mile markers, helping us measure the expansion of the universe. These projects are not just about crunching numbers, they're about empowering people to be part of something bigger than themselves. By participating, you're not just observing science, you're actively shaping it. Why does this matter? Because dark energy isn't just a problem for scientists in labs or observatories. It's a question that challenges our understanding of the universe itself, and answering it requires a collective effort. The more people involved, the more data we can gather, and the closer we get to uncovering the truth. Plus, citizen science bridges the gap between researchers and the public, making complex ideas more accessible and sparking a sense of wonder in people of all ages. As we look ahead, the role of citizen science in dark energy research is only going to grow. But what about the future of dark energy studies as a whole? What new tools and technologies are on the horizon, and how might they change the way we approach this cosmic mystery? Let's take a closer look at what's coming next. The future of dark energy research is brimming with potential, and the tools we're developing to uncover its secrets are nothing short of revolutionary. Take, for example, the Vera C. Rubin Observatory, set to begin operations in the next few years. This groundbreaking facility will map the entire visible sky in unprecedented detail, capturing billions of galaxies and tracking their movements over time. By observing how these galaxies are pulled apart by the universe's expansion, scientists hope to gather clues about how dark energy behaves on a cosmic scale. It's like turning on a high-resolution camera for the universe, giving us the clearest picture yet of this mysterious force. Then there's the Nancy Grace Roman Space Telescope, often referred to as the next-generation Hubble. Scheduled to launch later this decade, this space-based observatory will peer deep into the cosmos, studying the distribution of galaxies and the way their light bends due to gravity, a phenomenon known as gravitational lensing. These observations could reveal subtle patterns in the universe's expansion, offering new insights into whether dark energy has changed over time or remains constant. Imagine the possibilities. We might finally crack the code on what dark energy truly is, whether it's a property of space itself or something entirely unexpected, like a new force of nature. But the real excitement lies in the unknown. What if dark energy isn't just a single phenomenon? What if it's a doorway to an entirely new branch of physics, one that challenges everything we think we know about the universe? Some theories suggest that dark energy could be tied to the fabric of spacetime in ways we haven't even imagined. Others propose that it might interact with matter or even other dimensions. The next decade of research could bring answers, or just as thrillingly, even bigger questions. And here's where things get truly fascinating. As we push the boundaries of our understanding of dark energy, we're not just exploring the cosmos, we're also opening up new possibilities for life beyond Earth. Could dark energy influence the conditions needed for life to exist elsewhere in the universe? Or could it even play a role in how civilizations might evolve across the stars? These are the kinds of questions we'll tackle next as we dive into the intriguing connection between dark energy and the search for extraterrestrial life. As we continue to unravel the mysteries of dark energy, one question looms large. How does this invisible force shaping the cosmos affect the potential for life beyond Earth? The universe is vast, filled with countless stars and planets, but only a fraction of those worlds may possess the right conditions for life to thrive. Dark energy, with its relentless push on the fabric of space-time, could play a critical role in determining which corners of the universe remain habitable and which become too isolated or inhospitable to sustain life as we know it. Picture this: as dark energy accelerates the expansion of the universe, galaxies are being pulled farther apart. Over billions of years, this process could leave planets in distant star systems increasingly isolated, cut off from the resources and interactions that might foster complex life. On the other hand, some researchers speculate that dark energy's influence might also create unique environments where life could emerge in unexpected ways. Could there be civilizations out there thriving in conditions shaped by dark energy's effects, while simultaneously trying to understand its profound implications? This raises another intriguing possibility. Are there extraterrestrial scientists somewhere in the cosmos also puzzling over the nature of dark energy? If advanced civilizations exist, they too might be grappling with the same questions we are. How does dark energy work, and what does it mean for the future of their worlds? The search for extraterrestrial life might not just be about finding planets with water or the right temperature. It could also involve understanding how dark energy influences the broader cosmic landscape. As we ponder these questions, it's worth considering how dark energy's impact on the universe ties into another fundamental aspect of existence: time. What happens to the flow of time as the universe expands faster and faster? Could dark energy be altering the very nature of time itself? These are the questions we'll explore next as we dive into the fascinating connection between dark energy and the ticking clock of the cosmos. Time, it's a concept we often take for granted, flowing steadily from one moment to the next. But what if time isn't as constant as it seems? What if something as mysterious as dark energy could actually influence how time itself behaves? This idea might sound like science fiction, but it's a question scientists are seriously exploring. Dark energy, that enigmatic force driving the universe's accelerated expansion, might hold the key to understanding not just space but time as well. Imagine time as a river winding its way through the cosmos. Normally, this river flows at a steady pace, carrying everything along with it. But dark energy could act like a cosmic hand, subtly altering the river's current. On the grandest scales, this might mean time doesn't flow uniformly everywhere. In regions where dark energy exerts a stronger influence, time could stretch or compress, almost as if the river's speed changes depending on the terrain it passes through. This isn't just a poetic metaphor, it's grounded in theories that suggest dark energy could warp the fabric of space-time itself, affecting how time is perceived across vast cosmic distances. Some physicists propose that dark energy's influence might even create pockets of the universe where time behaves differently. In these areas, the expansion of space could cause time to slow down relative to other regions, creating a kind of cosmic time warp. It's a mind-bending idea, but it underscores just how interconnected dark energy, space, and time truly are. And while we can't directly observe these effects yet, they challenge our understanding of reality and hint at a universe far more complex than we've ever imagined. This interplay between dark energy and time also raises fascinating questions about the universe's ultimate fate. If dark energy continues to accelerate the expansion of space, could it one day alter the flow of time on such a scale that it changes how we perceive existence itself? It's a question that blurs the line between physics and philosophy, reminding us that the mysteries of the cosmos are as much about the nature of reality as they are about the stars and galaxies we see. As we ponder the profound ways dark energy might shape time, it's worth considering how this force also influences the very geometry of the universe. The way space curves and stretches isn't just a matter of shape, it's a fundamental aspect of how everything from galaxies to time itself fits together. And that's where the story of dark energy takes its next intriguing turn. So, what does dark energy have to do with the shape of the universe? Surprisingly, quite a lot. To understand this, we need to think about the geometry of the cosmos. The universe isn't just a vast, empty space. It has a shape, a curvature, and dark energy plays a starring role in determining what that shape looks like. Scientists describe the universe's geometry in three possible ways: flat, open, or closed. And here's the kicker: dark energy is the force that tips the scales between these scenarios. Let's break it down. Imagine the universe as a giant balloon. If the universe is flat, it's like blowing up a balloon just enough so that its surface stretches out smoothly with no curves or bends. A flat universe means that parallel lines will never meet, and the angles of a triangle add up to exactly 180 degrees. This is the scenario where dark energy's repulsive force perfectly balances the gravitational pull of matter, creating a cosmic equilibrium. Now, if the universe is open, it's like inflating a balloon so much that it stretches outward forever, curving away from itself. In this case, parallel lines would diverge, and the angles of a triangle would add up to less than 180 degrees. An open universe suggests that dark energy is so dominant that it overpowers gravity entirely, driving the cosmos toward infinite expansion. On the flip side, a closed universe would be like a balloon that's been deflated, curving inward on itself. Here, parallel lines would eventually meet, and the angles of a triangle would add up to more than 180 degrees. A closed universe implies that gravity could still win out, pulling everything back together in a cosmic crunch. But thanks to dark energy's relentless push, this scenario seems less likely, at least for now. So, how do we know which one we're living in? Observations of the cosmic microwave background, the faint afterglow of the Big Bang, suggest that our universe is remarkably flat. And dark energy is the reason why. Its mysterious force is accelerating the expansion of space, smoothing out any curvature over time. But here's where things get even more intriguing. This isn't just about geometry. The shape of the universe is tied to its ultimate fate, and dark energy holds the key to understanding how it all ends. Now, if you're wondering how something as intangible as dark energy can have such a profound impact, you're not alone. This brings us to the next piece of the puzzle, the quantum realm. How does the smallest scale of reality connect to the largest? That's where we're headed next. Now, let's take a step into the fascinating crossroads where dark energy meets quantum physics, a place where two of the most profound mysteries in science come together. Both fields are deeply puzzling on their own, but when we try to understand how they might interact, things get even more intriguing. One of the leading ideas that connects these two realms is quantum vacuum energy. Picture the fabric of space itself, not as an empty void, but as a seething, bubbling sea of energy. Even in a perfect vacuum, particles and antiparticles constantly pop in and out of existence, thanks to the strange rules of quantum mechanics. This phenomenon is known as quantum fluctuations, and some scientists believe these tiny, fleeting bursts of energy might actually contribute to the behavior of dark energy. Here's where it gets really mind-bending. If quantum vacuum energy is real, and there's strong evidence that it is, then it's possible that these fluctuations are somehow driving the accelerated expansion of the universe, the very thing we attribute to dark energy. Think of it like ripples on the surface of a pond, except these ripples are happening everywhere all the time, and they might be pushing the universe apart faster and faster. It's a theory that's still in its early stages, but it's one of the most exciting attempts to bridge the gap between the very small quantum mechanics and the very large cosmology. Of course, this isn't the only idea out there. Some researchers suggest that dark energy might be tied to the behavior of fields in quantum field theory, while others propose entirely new frameworks that could unify these two areas of physics. But no matter the approach, one thing is clear: understanding the connection between dark energy and quantum physics could be the key to unlocking some of the universe's deepest secrets. And speaking of unlocking secrets, this brings us to another intriguing concept, the holographic principle. Could dark energy play a role in how the universe encodes information on its boundaries? That's where we're headed next. What if the universe we see, with its vast galaxies and swirling cosmic structures, is nothing more than a projection, a hologram? This mind-bending idea, known as the holographic principle, suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional boundary, like a cosmic movie screen. And here's where dark energy steps into the picture. This mysterious force driving the accelerated expansion of the universe could hold the key to understanding how this holographic encoding works. At its core, the holographic principle challenges our traditional view of space and reality. Imagine the universe as a giant hologram where every star, planet, and even you are like pixels on a screen. The information that makes up everything we see isn't spread out across space, but is instead stored on the universe's outer surface. Dark energy, with its ability to stretch space itself, might be the force that keeps this cosmic projection running smoothly. It's as if dark energy is the energy source powering the universe's holographic display, ensuring that the information on the boundary stays connected to the three-dimensional world we experience. But what does this mean for our understanding of dark energy? If the holographic principle is correct, dark energy might not just be a mysterious force pushing the universe apart. It could be the glue that maintains the delicate balance between the encoded information on the boundary and the physical reality we perceive. This idea opens up entirely new ways to think about the nature of dark energy, suggesting it might be deeply tied to the fundamental structure of the universe itself. This speculative theory also raises fascinating questions about the limits of our knowledge. Could dark energy be the bridge between the two-dimensional boundary and our three-dimensional world? And if so, what does that tell us about the true nature of reality? While these ideas are still in the realm of theoretical physics, they offer a tantalizing glimpse into how dark energy might fit into a much larger cosmic puzzle. As we ponder the holographic universe, it's impossible not to wonder how time fits into all of this. After all, time is just as mysterious as dark energy, and the two might be more connected than we realize. What role does dark energy play in the flow of time, and could it hold the secret to why time only moves forward? These are the questions we'll explore next as we dive into the fascinating connection between dark energy and the arrow of time. What if the flow of time itself is shaped by the mysterious force we call dark energy? The arrow of time, the idea that time moves in one direction from past to future, is one of the most fundamental aspects of our universe. But could dark energy be influencing this flow in ways we're only beginning to understand? To explore this, let's start with entropy, the measure of disorder in a system. In our universe, entropy always increases, like a river that only flows downstream. This is why we remember the past but not the future, why a shattered glass doesn't spontaneously reassemble itself. It's the universe's way of keeping time moving forward, never backward. Now, here's where dark energy enters the picture. As the universe expands, dark energy is accelerating that expansion, stretching space itself. Some physicists suggest that this acceleration could be tied to the increasing entropy of the cosmos. Think of it like this: as the universe grows larger, there's more room for disorder to spread. It's as if dark energy is the wind pushing the sails of time's arrow, making the river of time flow faster and faster. And just like a river, once it starts flowing, there's no turning back. But what does this mean for the future? If dark energy continues to accelerate the expansion of the universe, entropy could reach unimaginable levels. Some theories even propose that far in the future, the universe might become so vast and disordered that time itself could lose its meaning. It's a mind-bending idea, a universe where the arrow of time no longer points in a clear direction. This connection between dark energy and time's arrow raises even more profound questions. Could dark energy be the hidden force that shapes not just the cosmos, but our very perception of time? And if so, what does that mean for our understanding of reality? These are the kinds of questions that bridge the gap between physics and philosophy, inviting us to think deeply about the nature of existence. And speaking of profound questions, what if dark energy doesn't just shape time? What if it also influences consciousness? That's where we're headed next as we explore the fascinating intersection of dark energy, the universe, and the mind. What if the very fabric of the universe, something as mysterious and pervasive as dark energy, could somehow influence the way we think, perceive, and even exist? It's a question that might sound like science fiction, but it's one that scientists and philosophers alike have begun to explore in recent years. Dark energy, this invisible force driving the expansion of the universe, doesn't just exist out there in the cosmos. Could it also play a role in shaping something as intimate as human consciousness? Some theories suggest that consciousness itself might be deeply intertwined with the fundamental forces of the universe. Think about it. Dark energy makes up roughly 68% of the universe, and it's everywhere, stretching the cosmos apart at an accelerating rate. If it's so omnipresent, could it subtly influence the way our brains process information, or even the way we perceive reality? Some researchers propose that consciousness isn't just a product of the brain, but could be a phenomenon that emerges from the interaction between our minds and the larger cosmic framework. In this view, dark energy might act as a kind of cosmic backdrop, a silent participant in the dance of thought and awareness. Of course, this idea pushes the boundaries of both science and philosophy. How do we even begin to measure or test such a connection? Could our perception of time, space, and even self be shaped by forces we're only just beginning to understand? These questions aren't just speculative, they challenge us to rethink what it means to be conscious in a universe that's constantly expanding, evolving, and filled with mysteries. But let's take a step back. If dark energy does have some connection to consciousness, what does that say about the nature of reality itself? Are we, as conscious beings, simply passive observers of the universe, or could we be active participants, influenced by forces we can't yet fully comprehend? This line of thinking opens up a fascinating dialogue between science and philosophy, one that invites us to consider how deeply interconnected we might be with the cosmos. And this brings us to an even bigger question. If dark energy is shaping the universe's expansion, what role does it play in the ultimate fate of everything we know? As we move forward, let's explore how dark energy might not just influence consciousness, but could also determine the destiny of the universe itself. The fate of the universe is one of the most profound mysteries we face, and dark energy holds the key to understanding it. Over trillions of years, the relentless expansion driven by dark energy could lead us to one of several possible futures. One of the most widely discussed scenarios is the Big Freeze. Imagine a universe that continues to expand forever, with galaxies drifting further and further apart until they're isolated islands in an ever-growing sea of darkness. Stars burn out, black holes evaporate, and the cosmos becomes a cold, desolate void. It's a chilling thought, but it's a possibility that aligns with what we currently know about dark energy's acceleration of the universe's expansion. Then there's the Big Rip, a far more dramatic and violent outcome. In this scenario, dark energy doesn't just push galaxies apart, it intensifies over time, eventually tearing apart everything in its path. First, galaxies would be ripped from their clusters. Then, stars and planets would be pulled apart. Even atoms and subatomic particles wouldn't be spared. The universe would end not with a whimper, but with a catastrophic rending of the very fabric of space-time. While this might sound like science fiction, it's a legitimate prediction based on certain models of dark energy's behavior. These scenarios aren't just abstract ideas, they're windows into the distant future, shaped by the invisible force we're only beginning to understand. And as we ponder these possibilities, it's impossible not to reflect on humanity's place in this vast cosmic story. What role do we play in unraveling these mysteries? How might our understanding of dark energy shape not just our knowledge of the universe, but our very existence within it? That's a question worth exploring further. The quest to understand dark energy isn't just a scientific endeavor, it's a profound reflection of who we are as a species. For centuries, humans have looked to the stars, driven by an insatiable curiosity to make sense of the cosmos. Dark energy, this mysterious force accelerating the expansion of the universe, is perhaps one of the greatest puzzles we've ever faced. And yet, here we are, using telescopes, satellites, and cutting-edge technology to probe its secrets. This isn't just about solving a cosmic riddle. It's about understanding the very fabric of reality and our place within it. What does it say about us that we're willing to dedicate lifetimes, resources, and boundless ingenuity to uncovering something we can't even see? It speaks to our relentless determination, our ability to dream beyond the limits of what we know. Think about it, dark energy doesn't directly affect our daily lives. It doesn't influence the weather, grow our food, or power our cities, but it challenges us to think bigger, to ask questions that stretch the boundaries of our imagination. In a way, the pursuit of dark energy is a testament to our humanity, our need to explore, to discover, and to make sense of the unknown. And as we inch closer to unraveling this mystery, we're forced to confront even deeper questions. What might dark energy teach us about the universe's ultimate fate? Could it reveal clues about the nature of existence itself? And perhaps most importantly, what does it say about our role in the cosmos? Are we merely fleeting observers in an infinite expanse, or do we have a unique part to play in understanding the universe's grand design? This journey isn't just about dark energy, it's about us. It's a reminder that even in the face of the incomprehensible, we have the courage to ask why and how. And as we continue to push the boundaries of our knowledge, we're not just exploring the universe, we're exploring what it means to be human. Now, as we wrap up this exploration, let's take a moment to reflect on what we've learned and why it matters. Because in the end, the story of dark energy isn't just a story about the cosmos. It's a story about us. As we come to the end of this journey, let's take a moment to reflect on what we've uncovered about dark energy. It's a force that defies our understanding, driving the universe to expand faster and faster, stretching the very fabric of space itself. From the groundbreaking observations of distant supernova in the late 1990s to the sophisticated missions of today, like the James Webb Space Telescope, we've made incredible strides in piecing together this cosmic puzzle. Yet, for every answer we find, new questions emerge, reminding us how much we still have to learn. Dark energy isn't just a scientific curiosity, it's a profound mystery that challenges our fundamental understanding of the universe. It makes up roughly 68% of the cosmos, yet we can't see it, touch it, or even fully explain it. What we do know is that it's shaping the fate of everything from the largest galaxies to the tiniest particles. And as we peer deeper into the cosmos, we're reminded that the universe is far stranger and more wondrous than we ever imagined. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That sentiment captures the essence of our exploration. Dark energy is one of those incredible unknowns, a reminder that the universe is full of mysteries waiting to be unraveled. And while we may not have all the answers yet, the pursuit of knowledge itself is what drives us forward. So, what do you think about dark energy? Does it leave you in awe, or does it spark even more questions in your mind? Let's keep the conversation going. Share your thoughts in the comments below. And if you're as fascinated by the cosmos as we are, don't forget to subscribe for more deep dives into the wonders of space and science. Together, let's keep exploring the incredible mysteries that surround us.